So in this video, we're continuing our test 4 review, and we're picking up with problem number 9. On a psychological test, a patient must match 8 terms with their pictures. We are assuming the same term cannot be used twice. In how many ways can this be done? So we have 8 terms and 8 pictures, and each term has to be matched with the picture, and our question is, how many different ways can this matching be done? Well, if we have, say, the first term, second term, third, fourth, fifth, sixth, seventh, eighth, so we have our 8th term. Well, the first term could be matched with any of the 8 pictures. And then now that picture is used, so the second term only has 7 pictures that it could be matched with. And then the third term could only have 6 pictures that it can match with. And then 5 and 4 and 3 and 2 and 1. So this would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 8 factorial. So there would be 8 factorial different ways that these terms could be matched with the pictures. So if I do 8 factorial, that is 40,320. So there are 40,320 different ways that the 8 terms could be matched with the 8 pictures. Now you might also think of this as a permutation problem. So this could also be thought of as a permutation of 8 items selected 8 at a time, or if you prefer this notation, 8 permutation, choose 8, and that gives us the same result if we were to type that in our calculator. So whichever way you think of this, this would be the result. Take a look at question 10. You are going to serve gourmet cupcakes at your college graduation party. The caterer has 12 flavors to select from. In how many ways can you select 3 of the 12 to serve? So we're selecting 3 of the 12 flavors. Now this is a straight combination problem because we're choosing 3 items out of 12. The order doesn't matter. It doesn't matter if you pick, say, chocolate first, second, or third. It just matters if it's picked or not. Same for, say, vanilla or strawberry or whatever. So, for number 10, we have a combination. Again, we have 12 flavors, and we're picking 3 of them. So that would be like this. Or, again, we could use the notation this way if we prefer. So if we do this calculation, 12, combination, choose 3, and that is 220. So there are 220 different ways that we could pick our 3 flavors out of the 12 flavors. Question 11. A password for a computer consists of 3 different letters of the alphabet followed by 2 different digits from 0 to 9. How many different passwords are possible? Now notice the words that it's 3 different letters. So we wouldn't be able to do AAA, for example, or we wouldn't even be able to do ABA. It's got to be 3 different letters, and when we choose our 2 digits, they have to be different digits, so I couldn't choose, say, 77. It would have to be 76 or something like that. I can't use the same digit twice. So our password is going to consist of 3 letters and then 2 digits. So how many different ways could we pick the 3 letters? Well, the first letter, there would be 26 different letters that we could pick from. Then there would be 25 different letters that we could pick from. And then there would be 24 different letters that we could pick from for the third letter. So there would be 26 times 25 times 24 different ways that we could choose the letters. Incidentally, That would be a permutation of 26, choose 3. So we could think of it as that permutation as well. Now we have to pick two different digits. So of the digits, there would be 10 possibilities for the first digit, and then there would be 9 possibilities for the second digit. So altogether, there would be 26 times 25 times 24 times 10 times 9 different passwords possible. Incidentally, that 10 times 9 we could also think of as a permutation of 10, and we're choosing 2. So we could do it like the earlier problem. I could find this permutation, I could find this permutation, and multiply those two things together. Well, whichever way you do it, if I take 26 times 25 times 24 times 10 times 9, that would be 1,404,000 different passwords that would be possible. So 1,404,000 different passwords are possible. Now, just for the sake of it, just to show you, if I take 26 and find the permutation, choose 3, that is 15,600. If I take 10, math, permutation, choose 2, that is 90. And if I take 15,600 times 90, that also gives me the 1,404,000. So either way we think of that calculation, it's 1,404,000 different passwords that are possible. Let's take a look at number 12. Number 12 says, use the 7th row of Pascal's triangle to find the number of 2-element subsets that can be chosen from a 7-element set. So we're going to pick 2 elements out of 7 elements, and the question basically is how many different ways can we do that? And so we're going to use Pascal's triangle to figure that out. So if I look at Pascal's triangle, well, we start with 1, that's row 0, then 1, 1, that's row 1, and then 1, 2, 1, the 2 is coming from 1 plus 1, remember, that's row 2, 1, 3, 3, 1, again, this 3 is coming from 1 plus 2, this 3 is coming from 2 plus 1, that's the third row, fourth row, 1, 4, 6, 4, 1, again, the 4 is coming from 1 plus 3, 6, 3 plus 3, 4, 3 plus 1. The fifth row would be 1, 5, 10, 10, 5, 1. So again, like the 10 here is 4 plus 6, the 5 here is 4 plus 1. The sixth row is 1, 6, 15, 20, 15, 6, 1. Again, the 15 is coming from like 5 plus 10, the 20 is coming from 10 plus 10, and so on. And finally, we're to the 7th row, so that's going to be 1, 7. Let's see, 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is 35. 15 plus 6 is 21. 6 plus 1 is 7. And we end in 1. So this is the 7th row of Pascal's triangle. So again, we want to use the 7th row of Pascal's triangle to find the number of 2-element subsets that can be chosen from 7-element sets. So the 2-element subset is going to be the second entry in the 7th row of Pascal's triangle. Now this is the 0th entry, this is the first entry, this is the second entry. So the answer is going to be 21. So there are 21 2-element subsets. And just to make sure that you're clear on this, if I have a set that contains 7 items, so maybe I have A, B, C, D, E, F, G. That's a set that has 7 elements. So if I am going to pick 2 of those 7 elements, how many different two-element subsets are possible. So like if I picked AB, AC, AD, BC, BE, and so on, there would be 21 different subsets that has two elements in it. That's the idea behind this. Incidentally, that would also be the combination of 7 choosing 2. So I could not use Pascal's triangle. I could find the combination of 7 choose 2, or again, I could write that this way, and that would also give us an answer of 21. So just to show you, that gives me the answer of 21. So if you'll remember, Pascal's triangle and combinations are very related. Let's take a look at number 13. So number 13, describe where the combination of 18 choose 2 would be found in Pascal's triangle. Well, that's a lot like the problem we just did, except we're describing this. So again, we're looking at the relationship here. Well, I just mentioned that 7 choose 2, that was the second entry in the 7th row. Well, 18 choose 2 is just like that. So the combination of 18 choose 2, that is going to be the second entry in the 18th row. So this would be the second entry in the 18th row of Pascal's triangle. Now we don't have to actually find that, we were just to describe where we would find it. So if I were to continue Pascal's triangle down to row 18, the second entry, and again remember the first entry there is really entry 0, so 0, 1, 2, so it would be like in the same place, but in the 18th row, that would give me the combination of 18 choose 2. Let's take a look at number 14. Number 14, we have two parts. We have part A and we have part B. We want to describe each event as a set of outcomes. So in A, when 3 coins are flipped, we obtain exactly 2 heads. So we want to actually describe the events as a set of outcomes. So in other words, we want to list all the possible ways that when 3 coins are flipped, we get exactly 2 heads. So let's do that up here, number 14. So basically we're looking at the set where we flip 3 coins and we end up with exactly 2 heads. Well, we could get heads on the first flip, heads on the second flip, and tails on the third flip. That would be one way that we get exactly 2 heads. We could get heads on the first flip, tails on the second flip, heads on the third flip. That would be exactly 2 heads. And we could end up with tails on the first flip, heads on the second flip, heads on the third flip. That would be exactly 2 heads. These are the only 3 ways that we could end up with exactly 2 heads on 3 flips of a coin. So heads, heads, tails, heads, tails, heads, tails, heads, heads. Those would be the 3 ways that we could end up with exactly 2 heads. And that was 14A right there. Now we need to look at B. So if we look at 14B, so again, we're doing the same thing. So we're going to list the set of outcomes. When 2 dice are rolled, we obtain a total of 8. So we need to think about how can we end up with a total of 8. Well, if one of the dice lands on a 1, then we can't get an 8. Because even if the second die is a 6, the sum of that would be 7, not 8. So if either die lands on 1, you don't get a sum of 8. But if, say, the first die lands on 2 and the second die lands on 6, that would be a sum of 8. So that's one possibility. Now, it's also possible that the first die could land on 3, and then if the second die lands on 5, that would be a sum of 8. It's also possible that the first die could land on 4, and then if the second die also lands on 4, that would be a sum of 8. It's also possible the first die could land on 5 and the second die could land on 3. That would be a sum of 8. It's also possible the first die could land on 6 and the second die could land on 2. That would be a sum of 8. And that's it. So the only ways we would be able to get a sum of 8 are these 5 ways that I have listed here. 2, 6, 3, 5, 4, 4, 5, 3, 6, 2. That's it. So we've listed all of the ways that we can get a sum of 8 when we roll 2 dice. Let's take a look at number 15. If a single card is selected from a standard 52 card deck, what is the probability that a red face card is selected? So we want to know, if we pick one card, what's the probability that it's going to be red face card? So we have to think about what a deck of cards looks like. So I'll bring in my deck of cards here. So first of all, we have a total of 52 cards, and we have face cards. And of the face cards that we have here, which is the Jack, Queen, and King, there are 6 red face cards. So the Jack of Hearts, Queen of Hearts, King of Hearts, Jack of Diamonds, Queen of Diamonds, King of Diamonds. There are 6 red face cards. So our probability is 6 out of 52, which we could reduce that. 6 and 52 can both be divided by 2. So 6 divided by 2 would be 3. 52 divided by 2 would be 26. So we have a 3/26 probability. Or if we wanted, we could write that as a decimal. 3 divided by 26 is about 0.115. So that would be approximately 0.115 for the probability. So I think we'll stop this video here. We'll pick up with problem 16 on the next video, and we should be able to finish through problem 23, the end of our sheet, in that video.